Hello, my name is Jordan Marcinkavage, EDM Applications Engineering Team Leader here at Makino Mason. Today we're going to talk about the EDAF3 synchro machine with a few additional options, mainly the Renishaw RMP 400 probe as well as an MMK tilt rotary table. After the presentation, we'll open it up for Q&A to answer any questions that you may have. During the presentation, if you have any questions, feel free to add them into the chat window. So today we're going to talk about the MMK tilt rotary table, the Renishaw RMP 400 probe, 6-point vector probing, and also our compensation method, the work installation error. One of the tables we commonly use on the EDAF3 is the MMK SAT 100. So this is a 15 kg table and it's fully integrated into the Hyper-I control, which means that all programming, chuck, clamp, unclamp, manual movements, everything is done at the control. So there's no need for an external controller. For the A axis, it's full rotation, so 0 to 360. The B axis tilt is plus or minus 110 degrees. This table is also compatible with Aero and System 3R pneumatic chucks. Other options are available, like part-specific chucks as well. And one of the benefits of using a pneumatic chuck like an Aero or System 3R is it also opens you up into possibilities for automation to be able to swap in and out fixtures fairly easily. For table placement, we're often placing the table in the center of the X stroke, like is shown in the top here. But depending on specific part requirements, we're also able to move the table location and orientation. And another important thing to remember is that this option isn't necessarily tied to the EDAF3 or the SAT 100 table. Depending on the part requirements, we can also facilitate the option on other machine platforms and the use of other tables as well. A few of the benefits of using a tilt rotary table on the EDAF are you can reduce the amount of part setups required, and instead of having multiple stationary fixtures for each machining vector, the part can be clamped one time and rotated and tilted to gain access to multiple machining areas and vectors. So for example, on the left, we have just an example of two static fixtures. The one on the left, fixture 1, which is used just to machine feature 1. Fixture 2, you can see the part is slightly tilted. That's to access feature 2. So basically you have two fixtures, one accommodates a separate machining vector. Whereas if you use a tilt rotary table, you can simply hold on to the part in a way that allows access to as many features as possible, and then just tilt and rotate the table where you need it to accommodate the different machining vectors. Also with this, you can reduce the amount of setup time or machine downtime. For instance, on the left side, those fixtures, to be able to mount the static fixture into the work zone, you might have to indicate the fixture in, pick up on the fixture, and things like that, which cause machine downtime. Whereas you don't have that problem with just using the tilt rotary table. So unlike the multiple static fixture method, you only have to set the tilt rotary table up one time and basically find your rotation point. So this creates less downtime and less setup time. And it also reduces the possibility of human error when setting up multiple fixtures. The Renishaw probe is fully integrated into the Hyper-I control, which means all programming, turning on and off of the probe, everything like that is done at the Hyper-I. So there's no need for any external controller. We also have Aero or System 3R tool holders to help with accurate, repeatable clamping of the probe itself. The benefits of using the probe is it allows for automated part pickup routines to reduce part setup time. You can also create customized probing routines such as part and fixture load verification as well. So as long as you have the Renishaw probe option and the tilt rotary table option, you have the ability to use 6-point probing. And 6-point probing measures the part alignment error using the part's 6-point datum structure. And by the 6-point datum structure, we're referring to the 3 points on the primary, 2 on the secondary, and 1 on the tertiary. And with probing, we use vector probing. So it gives us the ability to move the probe along a combination of X, Y, and Z directions. So we don't have to exactly move only in X, only in Y, or feed the probe only in Z. We can move in any combination of the three. And the probing process is an iterative process, which means it's repeated until the specified correlation tolerance is met. With our probing, we use ball probing, and sometimes we also use shank probing. So for ball probing, it's the standard form of probing where we're making contact with the workpiece with the sphere on the end of the shank. But it's also possible to use the shank to measure the part. And where you would do this is if you have a point that falls on a small radius, for instance, like on the leading edge. Sometimes it's more efficient to use the shank rather than trying to use a ball. So the linear and angular error are found during measuring. That's used to compensate the nominal machining locations. And with all this, it eliminates the need for the fixture to locate on the part datum set. And also, parts can be fixtured in a way that allows for maximum feature access. So basically, you don't have to fixture on the 6-point datum nest itself. So after we probe the part, we need to compensate for machining locations. So for this, we use our work installation offset, which is our 6-axis compensation method. So like we said, the 6-point probing can locate the part and determine the part's actual location and orientation. So in the picture here, the green model is perfect model space as programmed. And then the red is the actual location of the part that we found with probing. So basically we need to compensate to move our machining locations from the nominal out to the actual. So after we're done probing, we populate the data for the work installation offset used for the 6-axis compensation calculation. And for this data, it's shown at the bottom. So what we're looking at is the X, Y, and Z linear position of the part, or linear error, and also the X, Y, and Z angles, which would be the angular deviation about the X, Y, and Z axes. So with this, we have a total of 32 storage registers for parts with multiple datum structures, such as vane segments with multiple airfoils. And with this and the probing paired together, it really eliminates the time-consuming setup and operator part load error for complex shaped parts. The big thing is that you don't have to fixture or nest on the 6-point datum structure. You can hold the part in any way that you want that frees up access to machining features, and then you just probe that datum set. So now we're going to take a look at a video to show you an example of the 6-point probing and compensation. So the first thing we do is we have a part loaded into our fixture that has no part error. So it is exactly the same as model space. So you can see as we come down, our electrode falls directly into the cavity. So now we're going to put in some error. And so for here we have angular error and linear error as well. And you can see that the part does not line up, or the electrode does not line up with the feature. So now we have to probe the part and then compensate. So as we stated before, with everything being integrated into the control, ATCs, probe on and off, all programming, things like that. So after the ATC, the probe automatically turns on, and now we're going to come in and probe the part. So we're coming in, we're going to hit the tertiary, secondaries, and primaries. And you'll see that we have a different tilt and rotation for each one of these hits. That's done primarily just to show you that each one of these probe points, you can program any tilt or angle that you want, and we'll automatically normalize the vector with our macros. So once this probing is completed, we'll find our angular and linear errors. And since we have angular error in all three directions, whenever we see the actual compensation, you'll see a and B axes tilt to be able to compensate. So now after probing and compensation, we line back up with the feature. So now we'll go to Jake out on the showroom floor to give a brief overview of the option content we just discussed.
Thanks, Jordan. I'm going to give you guys a quick recap of what Jordan discussed. So first, I'm going to show you how we load a part into the row chuck. I'm going to clamp that. And also, while we're out here, we're going to discuss the Renishaw RMP 400 probe. And I want to show you how that is fully integrated into the Hyper-I. So as we stated earlier, the MMK table is completely integrated to the Hyper-I and also, of course, our hand pennant. So I can control the A and the B axis with the hand pennant here. So here I can rotate A, and then here I can tilt B. And aside from the hand pennant, if you look at our screen here, we're able to complete manual moves from this screen, and it displays the A and the B axis. So I can select from an absolute or incremental move, and I can also select if I want to work from a machine coordinate or a work coordinate. So I'm going to send A and B back to 0 for machine coordinate. So I'll type 0 in A, 0 in B, and I'll hit cycle start. Now as you can see, it's moving back, and that's how you complete a manual move from the screen. Now also on here, we're displaying our selected work coordinate, our machine coordinate. And you can see the symbol next to the A and B, and that indicates that A and B is actually at the home position. So we have our Renishaw RMP 400 probe. Up here is the receiver. Just a little side note, right now we have a pretty long stylus with a 6mm ball. This can be changed to any configuration you want. If you want a larger diameter ball, maybe a shorter shank, that can be changed out. And we have a calibration process that's going to automatically update things, such as the run out and the trigger delays for that stylus. So now I'm going to show you what a probing routine looks like using this blade here. So all I'm going to do is call up the program and hit start. So the first thing that's going to happen is the machine is going to do a tool change and grab the Renishaw probe. So you'll notice whenever this grabs the probe, that the probe's going to automatically turn on. Okay, now we know the probe is on because the lights are flashing. So now that the probe is loaded and turned on, we're going to position the A and B axis. And the first thing we're going to probe here is the tertiary. Now you'll notice that we're not probing in an exact X direction. That's actually a move in the X and Z direction. So we can probe on any vector that we want. And as we roll around the A axis here, we're going to touch the secondaries. And then after that, we're going to move on to the primaries here. Now you notice we're able to get all primaries and all secondaries without moving the A and B axis, and that is because we are able to probe on a vector. So that was one iteration there, and normally this will take maybe 3 to 4 iterations until it is solved, and that depends how big the air is in the part in the fixture. So as we're going around here, if you look on the screen, you can see that the touch probe light is on. That just indicates that the touch probe is on, and that is because we are fully integrated into the Hyper-I that we have these indicators. And you can also notice on the screen here that the touch probe light is lit up over here. So that button we can actually use to manually turn the probe on and off. And again, we'll let this run until it is solved. So now that we notice that Z is retracting and X is moving over, that indicates that the probing cycle is complete. And next it'll put the probe away, and then at this point we would grab our tool, our electrode, and begin the machining process. So now that we have completed probing the blade, I want to show you where those results are stored. So here's our work installation page. As you can see, as Jordan said earlier, we have 32 registers so that we can store multiple results. We selected to store the results for this blade in register 2, and as you can see that we have information for our linear air and our angular air. And this is the information that we'll use for our work compensation. So now I want to show you the program that was used to probe the blade. So right here at the top of the program is where we selected the register that we wanted to save the data into. And then below that, we have all the data for our 6-point datum structure. And just keep in mind that we can select any A or B position that we would like to use to optimize the moves to save on cycle time when we are probing. So that's a quick demonstration of the EDAF option with the MMK table and Renishaw RMP 400 probe. And now we'll go back to Jordan.
So in conclusion, just to go back over a few things that we talked about. We talked about the MMK tilt rotary table, the Renishaw RMP 400 probe, 6-point vector probing, and our compensation method of the work installation error. So all of this packaged together can lead to less setups, less amount of fixtures, also more flexible fixture designs. Since we don't have to locate on that 6-point nest anymore, we can locate any way that we want. There's also a less possibility of human error because you're not setting up multiple fixtures, multiple static fixtures for each machining vector. So now we're going to open it up for live Q&A to answer any questions that you may have.
Good afternoon, everybody. Jordan and Jake, thanks for joining us. To our guest, again, thank you for joining. In the Q&A section on the screen, please feel free to put any questions you may have. There are a couple that have already come in during the broadcast, but continue to do so. The first one that we got is as follows. Do you have to use 6 points for this probing and compensation method?
Yeah, so I'll take that one. So yes, you do need to use all 6 points to determine the part error based on the datum structure. And it is possible to use the probe for other pickups like centering or edge finds. It just won't utilize the 6-point compensation.
All right, thank you. And how do you set up a probe, or what does it take to set up a probe?
So whenever you get a probe, essentially all you're doing is basically first you're assembling the probe body into the holder for the EDAF, installing the probe stylus that you need. Outside of that, you're going to modify. We have a calibration program that we use. And we use this program to establish trigger delays and also things like probe runout. So you're going to modify that program, update the information for your different, for your new ball stylus, your stylus diameter. And then after that, we have a calibration artifact that we use. So essentially you're just going to run the calibration program after that, and then you'll be good to go to use the probe.
So relatively quick and out of the box.
Yeah.
Here's the next question. So can 6-point probing be used on machines that do not have tilt rotary tables?
So no, so we always use the tilt rotary table. It's for a couple of different reasons. The first reason is without the tilt rotary table, you may not be able to move the part around to be able to actually access all the points and vectors that you need. But also after you find your part error, without the tilt rotary table, you likely wouldn't have enough machine axes to actually be able to realign the part for the compensation.
Okay. Does it have to be that specific tilt rotary table?
No, the SAT 100 is just one that we typically use. But there are options depending on machine type, and part size, where we could utilize other tables as well.
Okay, thank you. And for the next question, how long does it take to probe a part?
So it's pretty much dependent on the part size, so the distance between the points, but also how many different tilt and rotary positions you have to be able to access each point with the vector. But essentially, like with a normal aero size part, like that small blade that we had in the video, or something equivalent to that size with a vane, you'd be normally looking around 3 to 5 minutes.
Okay, so pretty quick. Next question that came in is, what is the suggested total run out of the probe ball?
So normally we try to get the run out down within like a couple thou, but our compensation does have the capability of dealing with the error.
Okay. And so thank you. Also, what information is required to generate a program for 6-point probing?
For the 6-point probing, essentially it doesn't need a ton of information, but we do need the X, Y, and Z location of each point, the I, J, and K vector that's associated with the point, which would essentially just be the vector normal to the surface at that point. Then after that would be the tilt rotary positioning for each point as well.
Okay. So the next question we have is, let me read it. If the plunge direction normally has 3 components, right? X, Y, and Z, does the probing prove as effective as locating the part on its datum structure directly?
So I think that this is basically, if you're not doing just a direct Z burn or X burn or Y burn, but a vector burn essentially. But yes, from what we've done so far, it does work just as effectively.
Okay. So another question here, that on different parts that are not right blade or vane parts, like what we had here in the demo, if you can still use the probe on the hyper-eye control if the part surfaces are accessible with a stylus.
Yes. So you can still definitely use the probe to do things like corner pickups, edge pickups, centering, and things like that. It would just be a different type of compensation than the 6-point.
Okay. So, all right. So basically on like a non-5-axis EDM.
Yep.
Okay, great. Thank you. So that's all the questions we have right now. So let's give it maybe a second if anybody else has anything. I think not. So I would say thank you everybody for joining. Okay, will this presentation be available for download? Great question. If you come back to the Makino YouTube channel in a couple of days, that's where we post these and previous ECs. So go to YouTube, Makino Inc. We will post this one there, available for viewing anytime you want to, and all the previous ECs as well. So great question. Thank you for that one. So thank you again, everybody, and have a good afternoon. Bye-bye.
Thanks.
Thanks. Bye.